Hello, it's Keith here, and this is lesson 1 of the Maxtile series of my Z80 assembly programming tutorials. Now, what is Maxtile? Well, Maxtile is what you can see here on the screen. I've made two, if you could call them that, I've made two previous Tilemap examples. Now, the most basic one was in the Grime series, which was really a character blocks type system where everything had to be 8 pixel aligned, and it really only used a very small number of potential patterns. Very simple Tilemap though. I then did a series called Mintile. This was used by the Chibi Fighter game, and this allowed for X-flip, and it allowed for multiple banks of 256 tiles, and it allowed for a scrolling background Tilemap, but there were limitations with Mintile. It couldn't do Y-flip, and it also couldn't do more than 256 tiles, and there were some other limitations in there as well. Now, Maxtile aims to address all of the issues with Mintile. Maxtile uses 2 bytes per tile, so there is a potential of up to 4,000 patterns. There is also different drawing engines that are all optimized for the system in question. There's a platform-specific driver, and the various options are X-flip, Y-flip, X and Y-flip. There is also solid fill, so we can fast fill areas, and that is faster than using a tile pattern. There is also doubles height, which doubles the height of the source pattern data, effectively using half the amount of source bitmap data. It's intended to save memory, not speed. It would save a little bit of speed though on most systems, but it's intended if you want to fill a large area with graphics, but they don't need to be as high resolution. Halving the vertical height is a good solution. And you can see all of these on screen here. Here we've got a fast filled area. Here we've got a double height area. And also we've got various tiles here, and we've got X and Y flip going on here. Now you can see there's various objects moving around the screen because it uses miniature tile maps to simulate sprites. These are using the same graphics routines, and that means there's less to convert to port to different systems, because I've ported Maxtile to all of the systems in my main tutorials where applicable. It doesn't make a lot of sense on the NES, for example. NES only has 256 patterns, and it can't do X and Y flip for its patterns, so it doesn't really make sense to port to that system. But the example here does work on vast majority of my systems. Now you can see we've got some computer controlled characters, and we've also got a player sprite, and I can flip the player sprite around, which is showing off the flipping. The flipping of the pattern data is done in real time, so there's no extra pattern data for the X and Y flip. You can also see there's this pseudo transparent object moving around there. The pseudo transparency uses byte 0 transparency, as I call it. Basically, if a byte is entirely 0 pixels, the color 0 for an entire byte, then that byte is considered transparent and not drawn to the screen. The transparent routine doesn't support X and Y flip though. It's all optimized, so there's a lot of different code paths, and so doing X and Y flip on transparency would massively increase the code size. So that's what we're going to be looking at with Maxtile. That is not the example we're going to be looking at today. That's a little bit of a complex example. We're going to look at that next time. What we're going to look at today is the minimal example. Now here is the minimal example. You can see we've got a scrolling background. There's no sprites this time. This is what I use to test things initially and get all of the graphics routines working. The basic drawing routine is the most simple one, which is just an unflipped tile. And then we've got X-flip tiles, we've got filled tiles, we've got double height tiles. There's no transparency here. Transparency only makes sense for the sprites unless we had multiple layers going on, which would get very slow indeed. But so that's what we're going to be looking at today. That minimal example. Now, just before we do that though, I just want to discuss the sort of groundwork concept behind Maxtile itself. So Maxtile uses 2 bytes per tile for a tile pattern, whereas the original Mintile only used 1 byte. Now, the original Mintile had 2 tile maps. One was a cache of changes, and one was the source to fill that cache. Maxtile doesn't use 2. It only uses a single tile map, and it uses a single bit, which is the update bit or the dirty bit, depending on how you want to refer to it. So 1 bit defines if the tile needs to be updated or not. There's then 3 bits which define the mode. Then this is sort of normal, X-flip, Y-flip, and advanced functionality. And then all of the remaining bits are the tile number, and some of those bits could be used for things like bank switching or for color pattern palettes, depending on the system. But in theory, it allows us up to 4,000 patterns, and it's optimized for 16 colored patterns because the bottom 4 bits removed. This becomes an offset to the source pattern data for 16 color systems. You'd need to do some shifting for other systems, but that's what it's designed for. Now, the mode bits essentially work a bit like a binary tree. So basically the most simple one is the unflipped tile, and then this sort of branches out to the various more complex versions. There's a sort of detailed list of the possible options here, but we're not going to go into that so much today. What we're going to look at today is some of the core code of the minimal tile. We're not going minimal tile example. We're not going to look at the shared code yet. It's a bit too advanced to look at that yet. What we're going to look at is the shared code of the minimal example that's called test 1. So let's go over to the code and let's take a peek. So this is the test file that we will be looking at today. It's called test 1. Now most of the code that runs the example is in this. There is a small part that is contained within the platform specific example. This is Maxtile Minimal, this is the CPC version. But the vast majority of the code is shared for all of the examples, and that just makes it easier to sort of port to new systems, and also because the code shouldn't change between systems really, it's all in here. Now the first thing we're doing here is we're setting up the background memory address. Now we load HL with the address of the background tilemap, and then what we're doing here is we're loading that into the background tilemap base. Now this background tilemap base can be shifted to allow for horizontal and vertical scrolling. If we add 2, we will move across one tile. If we add the entire width of a line, we will move down one line, and so that's what we do there. We're also loading background tilemap width in here. Now this is in bytes, so the tile map is 36 tiles wide. Maxtile is designed for 32 tile wide screens, and there's a 4 tile scrolling area, so that's why we end up with 36 times 2, because there's 2 bytes per tile in the tile map. So that's what we're doing there. We're running set scroll to initialize the background. Now what we're doing next is we are loading the crop defaults here. Now the crop defaults change. Actually this isn't really used by this example, but the crop defaults are something that the main code needs, and this is used for detecting the area that sprites are taking up. So for completeness we're loading it here, even though this example doesn't really need it. We're then doing an initial draw of the screen here, and that will update the screen. Now one thing I should point out with regard to Maxtile is the way that the drawing works. Now there's 2 ways that you can draw to the screen. There is a very basic way and there's an advanced way. Now the basic way assumes that we're using double buffering, and it draws straight to the video memory. Now if we're not using double buffering, that will cause flicker. This is a very easy way of doing things for initial testing because it's much simpler, but the more advanced way doesn't require a double buffer, and it reduces the flicker to almost nothing. The way it does it is it has a cache, or actually 3 caches. What it does is it splits the screen into 3 vertical strips, and each of these has a separate cache, and any changes that need to occur to that area of the screen are built up in that cache and then all flushed in one go. Because they're flushed in one go, there's much less delay between removing and redrawing things, so the flicker is much less. And if we're really clever, we can actually synchronize the drawing of the thirds of the screen to the position of the raster, the CRTC raster, and that will mean that we can actually reduce the flicker to 0 if there's not much changing on the screen. So that is the advanced caching version. However, it's much more complicated, so as a beginning thing we often will just want to work with the simpler version and just use the double buffering, even if we haven't actually got a double buffering function enabled in our hardware. So we just unrem this, and that enables double buffered mode. Disable it, and the caching mode works. The caching mode is really the recommended one in most cases because it saves memory, you get almost no flicker, it's just more technically complex. Okay, so that's how our drawing works. Now, I should point out, as I say, this is a very complicated example. Maxtile is intentionally maximal. It's designed to do everything I could hope to do in a multi-platform game. So, as I say, take a look at Grime if you need something really simple. The Grime Z80 series will help you out if you want a beginner's example. Okay, anyway, that disclaimer aside, let's take a look at the main loop code. This is the loop that draws the background. So what we're doing here is we're updating scroll X, adding either 2 or 4. Now, we can move the background in quarter and half tiles if our hardware allows for it. Depending on the hardware, the CPC, for example, it's hard to move in quarter tiles. Moving in half tiles isn't so hard, but because of the optimization of the screen memory, we've actually got multiple versions of the code for doing those kind of shifts. So we might not want to do that. So we've got some options here, but we're updating the offsets in X and Y here. And then we're updating the scroll with either reset scroll, which is the advanced one for working with a full tile shift. So we're moving in tile 1 tile increments, not in 2 or 4 pixels. We're moving in full 8 pixel blocks. And this reset scroll will actually work out if after the 1 tile scroll, the old drawn tile to the screen and the new position the drawn tile to the screen are the same, because if they are, there's nothing to redraw, and so that saves a little bit of speed. But if we're moving in half or quarter tiles, we just have to redraw everything because it's too complicated in most cases. So we're just using set scroll, although the advanced example can use an LDIR command to do a bulk memory copy to effect a sort of half tile shift and things like that. It's very, very platform specific. It's a lot of work to get working, but it is possible. Now, once we've done that, we run the draw screen routine. This will either draw to the video memory directly or draw into the cache as required. So that's what's going to happen there. And then we're just looping indefinitely for the example to show what's working correctly. Now, the draw screen routine here, if we are using double buffering, there's nothing to do here. The actual reset scroll will have actually drawn everything to the screen automatically. That will have actually sent data to the screen. But in the other cases, what we need to do is we need to actually flush the caches to the screen. So we're loading IY with the address of the cache table, and then we're running fast draw caches. And now this will draw the caches straight away to the screen. It's referred to as fast draw because it's not trying to synchronize with the raster. That would take a little bit more time. So this is the simplest caching option. It's generally fine for all systems, to be honest. Waiting for the raster is a little bit slow, so it's not really something I would suggest you do. Speed tending to be quite important on these Z80 based systems. Now, recalculate scroll, what this does is it calculates the new background to tilemap base. The way it does this is simply to take the X position, multiply it by 2 in tiles. The bottom 2 bits are are in pairs of pixels, so quarters of a tile and halves of a tile, and so this 1 here is whole tiles, and we've got a potential scrolling area of 4 tiles because our tilemap is 36 tiles wide. We can draw 32, so we want an offset of 4 tiles here. So that's why we're taking those 2 bits there and adding that to our source tilemap data. Now, what we're then doing is we're taking the Y position and we're effectively simulating a multiply command here. We're effectively adding the width of the tilemap in bytes and repeatedly adding that to get our final source address for our tilemap here. So that's what's going on there. Now, set scroll here. This will actually redraw the tilemap. So what we're doing first is we're running that recalculate routine here to calculate the source address. We're then running reset tilemap. If double buffering is disabled, reset tilemap actually flags the tiles as dirty and needing redrawing. In the case of double buffering being enabled, then everything is actually redrawn every frame anyway, so that is not necessary. Now what we're doing then is we're running this cache tilemap CLS routine here. Now what this does is it effectively redraws the tilemap either to the screen if double buffering is enabled or to the cache if the double buffering is disabled. So that's what that does there. Now what we are looking at next is the reset scroll routine. This is the more advanced one for a partial scroll redraw. So this is if, for example, our tilemap has moved horizontally by 1 tile. Well, you'll notice that the vast majority of the tiles here are actually identical, and so moving to the left 1 tile, the old tile in this position, and if its neighbouring tile is the same, well, when it moves, there's nothing to change because it will look identical. And so that's what this is doing. It's detecting that, and in the case that that's the case, it is skipping over the tile. Now, because each tile uses 2 bytes, we're having to do 2 comparisons here, and we are ignoring the bottom bit because the bottom bit here is the dirty bit marking if a tile needs to be updated or not, because as I say, the tilemap is also the update, also has the update flags in that bottom bit, so that's why we're ignoring the bottom bit there. Now, if the tile does need updating because it needs to have changed to redraw the screen correctly, we are setting that bottom bit here which flags it for update when we run our drawing routine here. So that's what's happening there. Now, those drawing flags don't actually have an effect if double buffering is enabled, which is why we're not running that if double buffering is enabled. Now, the fast draw routines here are very straightforward. IY has been loaded with our source address of our cache table. So we're running get cache IY, which will get the source cache entries, and then we're running process cache. Now the get cache IY will set the 0 flag if there's no data to process, so otherwise we are actually processing that cache, but if there's nothing, we're just going to skip over it. We then move to the next cache and we repeat basically 3 times. All of the Maxtile examples use 3 caches. In theory you could use more, but I think any less will not have the desired effect, and if you had too many it would start to become so complex with the number of caches it would become impractical. Now the last thing we've got here is the actual tile map here. So this is the background tile map that's drawing this area you can see here. So we've got various sections, and this is intended so you can rem them out for testing. So this is filled tiles, these are flipped tiles, these are double height tiles, and just various other example tiles here. Now you can see there's a sort of template here, so you can work out what each tile is if you so wish. But basically, as I say, each of these tiles is basically defined here, and it's a different kind of drawing, as I say, as a test. So that's what we've got there, and that is all of today's example. So as I say, you can go to my website now, the source code and the build scripts. Maxtile is intentionally very complicated. It's a necessity for this because basically, as I say, I've got the grind series for a very simple example, Mintile for an intermediate example, so that all that's left to do is something that's very, very complicated. So that's what we've got today. Now, say you're welcome to use any of the code in Maxtile yourself. One thing I would say though is if you're at the level where you're wanting this kind of functionality, you might be best writing something of your own. So by all means, go to the website, download my source code, have a look at what I've done, and either decide that some bits are too complex for you and you're going to simplify them, or find better ways of doing things that suit what you need better. Just use whatever you can from my code in any way you can. As I always say, if you do manage to take any benefit from it in your own projects, you're welcome to do so. You don't need to give me credit even if they're commercial. Just take advantage. That's what it's there for. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.